Okay, so we're going to talk a little bit about why killer robots are a concurrency problem. And we're not like the guys after lunch. These are not real robots. So I'm going to start with a story. About a year ago, Stephan said to me, I'm learning Go. So my background's video games, console video games. I'd heard of Go. I knew its existence. I knew a little bit about it, but I knew almost nothing. I thought, oh, that's cool. He's learning Go. And then he said to me something that a lot of people ask me about and talk to me about because I've been in the game industry a long time. He said, oh, I always wanted to write a game. So that's cool. Yeah, lots of people like writing games. And then he dropped the bombshell. He said, I want to write a game in Go. We should write a game in Go, which spawned an instant negative reaction from me. I said that's absurd. I come from console game background. We write console games in C and C++. That's how you write console games. No one writes games in Go. That's absolutely crazy talk. We have this real historical worldview of how games are made, and it doesn't really quite gel. Go is firmly in that not games category. Very biased worldview. Kind of led me to pigeonhole the language a little bit, and so I said to him something pretty, retrospect, a little bit silly. I said, it's like Java. No one's made a successful game in Java, right? So I started throwing a whole bunch of questions at him. I said, I wanted to know about all the different bits and pieces of Go that I just assumed wouldn't fit for making video games. I was like, does it have good math libraries? I don't know. Does it have good physics libraries? I'm pretty sure it doesn't. I was pretty confident in my historically based opinions that Go was pretty terrible at all of these things that we would need to make a game. OpenGL bindings. And to be fair, Stephan came back with pretty decent answers on a lot of these things. He was, there were young implementations. It's a new language. There's lots of these things do exist. Some of them are in infancy. They're GUI. Their input management. Can we hook up a gamepad? Can we do stuff like that? And then this back and forth whether I would challenge his belief that he could build a game in Go, and he would, try and argue for it. And then I fell into his trap, and I said to him, well, concurrency is a hard problem in games. How good is Go at concurrency? So then we decided to make a game. We had to get a few constraints out of the way first. So Stephan and I both have full-time jobs that are not related to writing games in Go. So we wanted to, do something simple, do something that was fun that we could do in our spare time. But what should that be? So according to my 3-year-old son, robots are cool. So that got me thinking about a game that I played back in 1996 when I was in college. A friend of mine made it. It was a game about robots. It was a game very much geared towards programmers. The game looked like this. There were dots, and there were smaller dots. It ran in DOS, and you wrote little pseudo-assembly code to program your robots, and you loaded up all your robots into this executable, and they fought. They just battled it out until last man standing. And I thought to myself, I remember loving that game. I thought that was a lot of fun. I always wondered what that game would look like modern day and modern technologies. So I suggested this to Stephan, and he liked the idea. It took me a while to convince him not to make a Zelda clone, but we settled on robots. So 2014, we'd make this game. Obviously, it's going to be web-based because, it'd be fun little side project. We know how to write stuff on the web. If we're going to make robots, we have to have some sort of WebGL visualization. And they're obviously going to talk over WebSockets because let's throw as many modern, buzzwordy terms as we can at this little project. And we're going to need a server. And it started looking more and more like this is exactly where we should focus our efforts and build something cool in Go. So what did we build? Well, still in its infancy, but this is kind of a a basic visualization of what we've got. This is the modern version of dots and smaller dots. We've got a game server written in Go, and then we've got a protocol that you can talk to the game server, which is basically your robot gets a JSON blob of world state as it knows of what it knows about the world, and it sends back instructions. And the game server runs its little simulation, and it sends back world state. You write your robots in pretty much anything. We've got a web interface that lets you write JavaScript robots. We have some robots implemented themselves in Go, and you can set your robot's properties and do all sorts of fun stuff. Some of it works, some of it doesn't. We're still working on it. And then you get a visualization of the game. You can watch your robots blow each other up. So I'm going to talk about two aspects of the game today. We're going to talk about the architecture and how kind of the fundamentals of Go helped shape how we built the game server. And then Stephen's going to talk about the bandwidth and the serialization that we did. So starting with game architecture. I wanted to focus on this idea of a robot protocol, the client talking to the server and everything surrounding that interaction. The game server talks to a robot. There's lots of robots in a game, but what is the simplest form of the interaction? And that's just this instruction goes one way and game state comes the other way, and we want it to happen as fast as possible. So inside the server, we have our core simulation, and then we've got this chunk of code that handles player management. This is who's connecting, who's disconnecting, who's alive, who's dead, and what each person can see in the world. And then for every player, we have to serialize that data out and send it over the wire to them. It's all logic without display. There's no OpenGL needed. This is a completely headless server process that only does the game simulation and the serialization. So we didn't need all the OpenGL input, game management. That's all driven by the robots on the client side. But it gets more complicated because we don't want one server running one game. We want lots of games. We want this to scale really well. And this is starting to look a lot like a concurrency problem. So drill in a little deeper on just one of the robot interactions. We kind of broke our game server into two pieces. There's the stuff that has to run like accurately and solidly. That's the simulation logic. It runs at 60 hertz. The robot simulation sits there and it listens for whatever the latest instruction for each robot. It runs the simulation, and then it updates the game state. That has to happen on a fixed time step. We don't want that to be impacted by any network traffic latency or anything like that. And then we've got this other stuff that we want to run as fast as possible, but it doesn't have to be 60 hertz. It's going to be impacted by the connection between the clients. And that's going to be taking the game state and filtering it out to what each player can see and sending over the wire. So as it turns out, Go makes it really easy to separate this out. We find ourselves just naturally falling into this implementation pattern based on the Go paradigms, which kind of surprised me coming from a C++ background, and especially a console game background where we tend to build things in one big loop and then freak out because it's not fast enough and try and figure out how to make things parallel. Well, we started building this in Go, and things just sort of fell into this structure where we had set a Go routine that covers our game logic, one for player management, and then every player gets their own Go routine to handle serialization back and forth on their WebSocket. And we communicate through buffer channels, pushing the game state in one direction and instructions in the other direction. But there's a little bit more to the system than just the interaction between the robot and the game server. There's also how do we actually control the game server. So that's where we spun up yet another Go routine in our server to handle kind of higher level control logic. Start a new game, stop a game, set the game parameters. So our structure of our server kind of looks a lot like this. We've got one HTTP server running on a Go routine that just listens for instructions. You tell it to start a game, and it spins up this whole instance of this 60 hertz logic loop, and player management code, and then a whole bunch of different different players connecting and being serialized in their own Go routines. So coming from my game development background, it really surprised me how just the fundamental features of the language kind of steered us down this real highly concurrent path, and just the features fell out of the language choice. Anyway, so I'm going to hand over to Stephan now. He's going to talk a little bit about this column, this rightmost column of player serialization. So, Stephan, all yours.
Okay. So I didn't come planning on dancing for anyone today, and I haven't done it in 7 years, but the gauntlet has been thrown down. So here I am. This is a move from Samba, I think. It's been a long time. So just go like that. This is easily the largest crowd I've ever performed for. So thank you. I'm glad I went with that. I also have always wanted to fly. I don't think I could have demoed that as well. So thanks, Fraser, for that, for the description of the architecture. I want to talk about two things today. I want to discuss, I want to eventually get to a demo of our game. But first and foremost, I want to talk about some technical issues that we came across and how eventually, by following Go idioms, we were able to solve those in, I think, a pretty good sort of way. So here's a diagram of our game server, traditional game server. And there are two types of clients. There's the spectator and the player. And what they have in common is that every so often, right, we send out a packet of world state. Oh, here is everything you need to know about. Here are the robots, projectiles, et cetera, et cetera, et cetera. And there's one main distinction between these two types of clients, and that is that the players can also periodically send instructions. So instructions are things like, oh, I would like to move off of the stage, or I would like to shoot a bullet at the Wi-Fi in the hotel, whatever it is. So, and these are asynchronous. So you do it once, and well, it's asynchronous, and you can set it and forget it. So you basically tell the server, hey, I want to go to this location, and you don't have to worry about saying it every single update, right? So these are by nature small. That's kind of the good news. It's a little bit more chatter, but it's not really too big of a deal. So I'd like to put up on the board a dramatization of the game. Let's pretend that you're the blue player, okay? And something that kind of fell out of our game design proper was that, the spectators are seeing everything. Well, each player has an allocation of points, and you get to decide, okay, these points I want to give to my guns. I want them to be really nice and strong, or I want to be really fast, and one of them is a scanner radius. So you're only actually allowed to see what's going on a certain distance away from you. And this ended up being a really trivial and nice optimization for payload size based just on the design of our game. There's obviously the shared worst case scenario. If everybody and all objects and everything are within your scanner radius, then obviously you're going to have the worst case scenario. And it's not fair for us to just design to a best case scenario. So let's talk about the worst case scenario. Let's talk about the spectators. So the spectators basically see all the things all the time. They see all the robots, projectiles, explosions, building, messages. It's a lot of stuff. In fact, one of our really early implementations I was watching the bandwidth going out, and it was like 20 megabits a second. So you're like, 20 megabits a second times, seconds in a day, times, and bandwidth cost is like $7,000. And so I don't know how many of you are from the Bay Area, but for those of you who are not, that's significantly less than what you get in funding for a hobby project. So we had to kind of figure out what we were going to be sending and how we were going to send it. So I want to put up on the board one of our basic primitives that we use in the game. And this is the point. And it's just very simple, right? It has an X location, a Y location. And one of the things that I really liked about Go when I came to Go was that there's this awesome JSON marshal, and there are good introspection facilities. And so I'm able to create a point, pass it into JSON.marshal, and out come bytes that I can send over the wire. So here's our initial implementation. You can see the JSON there, and there are 47 bytes in that part of the payload. And we asked ourselves, well, can we do better than that? And if we're willing to kind of drop the structishness of this and kind of have some implicit meaning in the data, we could do something of this fashion, where basically our point struct grew this as array method, and then you could basically, whenever you needed it, you can say, oh, well, let's just give this slightly more compact version that's smaller, 39 bytes. But this had some problems, right? It was the way we did it, right? We had to adjust the board state as it went out to the clients, which was maintenance overhead and what have you. And we'll get to what we think was a better solution in a second. The other thing was we're not trying to put people on Mars, and it's just like these imaginary robots. Why would we have like float 64s? So we tried this, right? Oh, let's convert the type to float 32. And if you look at the payload, that's actually pretty good. We're less than half the size of what it used to be originally. And we're like, okay, well, mission accomplished. But there were some problems with this method, right? Namely, like the maintenance overhead. But more specifically, every time we would edit our code and compile, we had compiler warnings or compiler errors about type mismatching, right? So this was fairly annoying. And so we wanted to have it all. We wanted to have that smaller outgoing payload and also have what we had in the beginning just using Go structs, which was, oh, I want to take this thing and dump it into the encoder and have it come out nice and tiny. And so on our winding path to the final solution as amateur gophers, I kind of learned about and discovered deeper meaning, I guess, in interfaces. Interfaces, for whatever reason, I think maybe it's because my background is primarily in Python, I didn't really grasp the power there the first time around. And I'm going to just take a little diversion and talk about interfaces. It seems as though there was a kind of impromptu hands-up survey before about who was new, and hopefully this is going to be valuable to people in the community who are here for the first time and kind of learning about Go. So thanks for being here and welcome. So here's a sample interface, right? Really easy to do. You name it. This is the Gopher interface. And it's basically a collection of functions or method signatures that your type needs to implement in order to be used in certain places. And that second half is really what I didn't understand. In fact, from the docs say it best. It says, if something can do this, then that thing can be used here. So let's go back to our point primitive, and let's make it a gopher. And all I had to do is just add this squeak method. And as you can see, you can create a point and have it be of type point, or, and the second thing is really what I didn't understand, was that you can actually make a point and have it be of type gopher, which is more powerful in situations like this, where you make a point and you pass it to a function here that takes a gopher. So as I was learning more and more Go, I was rereading the JSON documentation, and I came across this bit, where value in this phrase is the value that you're passing into the JSON.marshal function. It says, if an encountered value implements the marshaller interface and is not a null pointer, marshal calls its marshal.json method to produce JSON. Can I do something with this to get all my goals, right? And sure enough, this was the thing we did. All you had to do is implement this one method to make it fulfill that interface, and it sent everything out as it was supposed to be. And I like this because you can basically deal with this in kind of a Unixy pipe-ish sort of way, where I'm still using JSON.marshal, and I'm just in midstream changing it, and out it goes. And our code went back to, oh, well, here's the board state just as it always is, and we're just going to marshal that and let it out the back end. So the world was better. And of course, we had to ask ourselves, well, what could we do better than what we currently have? And because I really like Go, I was like, well, I wonder if there's some sort of a binary encoding that we could use to make the packet smaller, make the chatter easier. So I looked in the standard library, and I found something called the Go binary encoding format. I'm unclear on the pronunciation, so I'm just going to go with Job. So we added Job serialization to our client and our server, which was the way I did it originally, and it got squished out of the branch because it was really ugly, was JSON.marshal was so trivial and so easy for me to use that that's what I had everywhere that we were doing JSON marshaling. Well, JSON package also has one called where you create an encoder, and you use that encoder's encode method. And Gob sticks to only that. Gob doesn't have a doesn't have a Marshall function. So basically, I was like branching on a string. I would go and do the old stuff here. If it was JSON, I would do the new stuff, with the Job encoder. And it was just kind of messy, and I realized that I'd made a huge mistake. And so I looked in the standard library to see if there's anything that could help me there. And so a package up, there's a thing called the encoding package, and it's got a handful of interfaces, which I thought, oh yeah, this looks great. This looks like it could help me. Except for I've got both a text marshaller and a binary marshaller, and that's kind of what I'm trying to use. And so there's not like a generic marshaller interface. Fortunately, if you do stick to the convention of using like JSON.new encoder, Job.new encoder, then you can then they have they have that similar signature of encode. And interfaces in Go are super easy to do. And so I just created this little one right here, type encoder. And you can see I still branch on the encoding type when I'm creating a player. But once I've assigned that encoder to player.enc, then I can use it down there. And that was where all the huge branching and ugliness was. And now it's just a single line, and it does the right thing. So there are obviously other projects they've actually spoken about at the conference in this space, Protobufs and Captain Proto, which they do things in different ways to achieve very, very interesting results. I suggest looking into them. And after doing this, we found that the general chatter was about half to a tenth the size of what it was previously. So we thought it was a pretty good one. And now we'd like to do a demo. If I can figure out how to do this. Cool. It's not showing up. Oh, you got a mirror displays. All right. It's funny because I'm the Linux guy.
Okay. So yeah, this is what we showed earlier, and this is all running locally. Let's make sure it's still running. Yep. So it's not running.
It's not running. I'd like to blame the Wi-Fi, but it's totally my fault, I guess. Do you want to talk about it a bit, and I'll see what's going on?
Oh, that's because it's crashed.
Oh.
Here, you do it. You fix it.
Okay.
Server's dying.
Oh, the server is dying. How do you switch to the... Anyway,
There we go.
oh, okay, perfect. Go ahead.
There we go. So there's our robot. This is our robot called Jimmy. He's written in JavaScript. All these other robots he's fighting against are written in Go. So Go versus JavaScript in a battle to the death here. Yeah, we're just, you can see with the JSON being sent across the wire pretty speed. This is what the JavaScript code receives, and it sends back some instructions. And GL rendering of the world state. You can see the robot increasing and decreasing his scanner radius as things pop in and out of the world. So. And then servers just sitting there, and other robots can connect and disconnect and come in. There we go, I think. Any questions?
That's it.
How did you guys manage to keep the simulation logic running at 60 hertz no matter how many players there were? We have a similar, at work we have a similar problem, and we're having like trouble with that.
So there are, we're not advertising that we can support like trillions of players in this game, unfortunately. I mean, Go is awesome. Don't get me wrong. We found, I mean, there are some like big O, N squared sorts of things going on with collision detection and what have you. And we found that we can scale up to about, I don't know, 16, 32, 64-ish players per game, and scale across with tens of games. It's just that we cap out at about 32. I don't know that we've done anything special with it.
Hey,
Hi,
quick question. What are you guys using for physics? Was there any existing libraries, or did you write your own from the ground up?
So we wrote a really simple 2D vector library, and we're going to open source that, right?
Yeah.
Yeah. We just maybe tomorrow we'll
It's
write
all
some
vector-
documentation
vector-based.
for it tomorrow in the hack day, and we'll open source that. And it's just basic vector stuff, and then our own collision detection and physics simulation that we wrote ourselves. So
Cool, thanks.
No worries.
One more quick question, guys. You just talked about reducing chatter, and you showed examples with Go binaries. I call them gobs. And also cap and
That's how it's said.
Well, that's awesome. And then cap and proto, but then your client is web client as well. So I was wondering if you wrote like custom.
So I wasn't very clear. So there's a step in the negotiation, the protocol negotiation, where the server says, "Hey, I support these things. What do you support?" And the client says, "I support these things." And the server chooses the most compact format of them all.
Okay, so you could just encode
So JavaScript just says, "I do JSON," and in a way it goes. We looked initially at trying to get some sort of a JSON gzip sort of a thing going between the server, but this seemed.
Thank you.
That's it. Thanks.
thank you.